Well, welcome everyone. It's an absolute pleasure to be here today. This is a very special day for KULR. It's also a very special day just for me as a Houston native to see the journey KULR's taken, and as we've opened up shop here and now to be surrounded with past colleagues of mine. So for those of you who don't know, I spent the first portion of my career at NASA Johnson Space Center, along with a number of my colleagues who are here in the room with me today, working for KULR now. Where we gained our tutelage, our learning, our understanding of batteries, battery safety for human spaceflight. And so we've had the privilege of taking that private side, which is what we're here to do today. I guess I need to back up just a little bit and say, hello, my name's William Walker. Introduce myself. I'm Chief Technology Officer here at KULR Technology Corporation. So with that said, I have a really fun job today, which is to highlight the technologies and products and programs that we've been developing. In particular, we're going to focus on what we're doing here at our headquarters in Webster. I think if you have two key takeaways from our discussions today, there's two key areas we're going to highlight. The first being battery safety, design, testing, and analysis. What are we doing here to provide solutions and services for that? And then the second area being safe transportation and storage of batteries. So ultimately, no matter how well you design a pack, ultimately those packs are going to reach the end of their life, or they're going to get damaged, or they're going to have to be stored. You need to do something about that in a safe way. And so we have a number of products that we provide that do that. But what I hope to do throughout the day, and what I hope that the team will demonstrate with the demonstrations that are going on this afternoon, will really give you an idea of not just, oh, wow, gee whiz, here's a product I can go online and buy, but the science and engineering that went behind that, and what we're doing here to continue learning about battery safety and to drive our products to the next level. So what I'm going to do over the next 30 to 45 minutes is talk you through a bit of a roadmap. I'd like to show you where we were, how we came to be, how we're focused on batteries right now, and Michael got into that a little bit with his talk. And then through that, I want to show you a little bit of the areas that we're going to be focused on in 2025 to give you a sense of why did we build everything that we built right here? What do we intend to do with it now that it's built? So if we just take a quick step back in time, and I understand with the screens, the text is small, so don't worry about that. I'm just going to walk you left to right. KULR has a very, very lush history. So over the course of the last decade, or I'll say starting next year, the last decade, from founding to now, we've been developing tools, technologies, products, and platforms to service energy storage. Now, if you go back to when KULR was founded, we were really a thermal management solutions company. Mike Carpenter here in the back, our Vice President of Engineering, who focuses on the thermal solutions, was a part of the predecessor company, ESLI. But what happened is we took those technologies, continued to commercialize those, and in parallel, KULR spent time using and applying those technologies to support the energy storage industry, developing new and similar technologies to support the energy storage industry. Over time, and over the last decade, KULR invested in acquiring IP from NASA, such as the internal short-circuiting device, which we use to trigger lithium-ion cells into thermal runaway to aid in pack level evaluation to abuse. Invested in various testing technologies that you use to characterize and understand thermal runaway, and then invested in developing our own solutions for thermal runaway, such as our thermal runaway shield. Additionally, in that time frame, those technologies were applied to develop our SafeCase platform, or our safe storage solutions, to provide a storage platform. So now we get to about the 2022-2023 timeframe when it really started clicking, the gears started turning, that we have all the parts, pieces, and components that we need, not just to provide a component or a service or a singular solution, but to also provide a total solution, a system-level solution. And so in the 2022 to 2023 timeframe, that's when we started moving forward with developing total solutions for energy storage. At the time, we went into CES 2023, and we referred to this as KULR One. So if you go on our website, if you go through our marketing materials, you hear KULR referring to KULR One. I think I can honestly say at the time in 2022 and then moving into CES, we were still learning, what did that actually mean? What was it for us? Was it going to be a micromobility battery? Was it going to be a space battery? What was it going to be? But what we did know is that the mentality was going to be consistent throughout all of that, which was we were going to focus on a safety-first battery platform. We believed that the e-bike battery fires that you see, the micromobility battery fires that you see, or all the way up to some of the larger fires that you see with cars, automobile vehicles, really it's unnecessary. We believe that if you take a safety-first lens at the get-go with your design, that you can achieve a safe design at a good price point price point that the customer will accept. And so that was a vision that kind of built itself into the philosophy that we as a team now know today as KULR One internally. Moving out of that, we come to 2023. We are executing on DoD-focused energy storage platforms. We're executing on space battery platforms. And so that really opened the door for KULR to say, okay, we're going to take the KULR One philosophy. We're going to have the KULR One Space, where we're focused on space batteries. We're going to have the KULR One Guardian, where we're focused on DoD architectures. And then now part of what you'll see today is our KULR One Air, where we're focused on silicon anode-based platforms for eVTOL. So we'll talk about all of that. So 2023, we're focused on batteries. I was located here, as were a number of our testing team. It was a little bit easier for us to do the testing portion of our business in Texas. We had opened up a small shop, and we began a slow transition of our battery services to the Texas area. Now in that 2023 timeframe, we had this kick up of our battery design programs. So we onboarded an engineering staff here to support those programs. That led us to requiring a larger infrastructure, which is where you're here to visit today. Moving into 2024, we took that, we expanded into this facility. We expanded our testing capability, our design, prototyping, fabrication capabilities, relocated our headquarters here. That happened just a few short months ago. And now moving into 2025, what I hope you'll take away from today, what I hope that you'll see is a renewed focus on battery production and additional testing services, as well as qualification and acceptance testing of those batteries. So we focused a lot early 2023 on the prototyping, rapid development. Now we're moving into qualification, production, all under one roof. To do that, we built up a stack of, I would say, really talented individuals. So I would say I have the good fortune of being surrounded by a team of very talented engineers, technicians, quality personnel, operations personnel who are dedicated to the KULR mission, who are dedicated to our customers and getting it done every day. We built up 6 key technology domains around this group of people that we use to drive revenue for the company. The first 4 of which are what we're going to focus on today, which is what we're doing here at our headquarters. So the first is battery design and analysis. So again, kind of go back to those early days. We built up a team. We were building a team that can do of experts that can do the battery design. They can build prototypes. We can design anything that can be manufactured and built just from a prototype perspective. Do all the modeling and analysis, thermal desktop, console, GT suite, you name it. So we do all that. So we built up a core team of engineers that can provide for that technology domain of just simple design and analysis. Additionally, in the recent 3 to 4 years, we've been onboarding testing technology. We started with a bomb calorimeter, which for those of you who don't know, for decades now, the bomb calorimeter has been the industry standard, the bread and butter for thermal runaway characterization. It goes all the way back to where scientists and engineers were analyzing the individual materials that would go into a lithium-ion cell to characterize the decomposition of those materials. It since was expanded and now used for cell-level testing. So that's where it really started for us from a testing perspective. We very quickly after that onboarded the fractional thermal runaway calorimeter, which as Michael alluded to, I'm a co-inventor on. Several of the other co-inventors couldn't be here today because they're actually in France using that same calorimeter to do X-ray transparent experiments at a synchrotron facility. So not just in private industry, but the calorimeter lives on for NASA. We also onboarded some of our very own testing techniques. One that you'll see today, live demonstration, which is our impingement zone mapping technique, or IZM, which allows us to characterize the ejecta that's coming out of the cell. So when you see a battery fire go off, there's a lot of junk that comes out of it, a lot of gases, solids, liquids, and gases, combustibles, and you can have a fire. And so we characterize that with our IZM. And then, of course, we have electrical testing, pack testing, you name it, we do it here. That's our second core domain that we're supporting in this facility. The third is the new one. This is what we've really been onboarding in this facility over the course of the last 12 months is production capability. What we focus on here is production for low volume quantities of custom boutique batteries. So what we're trying to do is provide solutions for building out a capability for doing production on, call it hundreds to low thousands of batteries from a single room in an AS9100 certified environment, all under one roof. So we've been building up production capability, onboarding our AS9100 certification, as well as building out a clean room or production room that you'll get a tour of later today. And then some of the acceptance testing equipment that you require. So, you build up a battery, you kind of got to check out and do various testing on it before you actually ship it to a customer. So adding that into our production capability. So you'll see a little bit of that today. So that has become, I would say, our most recent core technology domain, and that'll take a big highlight for us in 2020, in 2024, end of this year and moving into 2025. And then the fourth area that we'll discuss today is battery safety as it pertains to storage and transportation. So one of our heritage, or what we call our legacy products, is the safe case. So KULR, as I mentioned, we had thermal technology and IP that we had developed that can mitigate and extinguish thermal runaway. Work was done early on to integrate that into a containment system that we refer to as safe case. We've since taken that to the next level to be able to do total containment of total propagation events and have commercialized that for use. We have various DOT permits on that. The design work that continues, the expansion of how big these cases are and total capacities that they can contain. The work for that is also done here, and that's our fourth core technology domain. And then the other two that are still hosted out of our Shawline branch that Michael mentioned earlier, we continue work with our thermal technologies, our legacy technologies, with PCM heat sinks, FTI thermal interfaces, and then of course the sixth technology domain being expertise in vibration reduction technologies with our KULR Zero Vibe and the KULR Vibe platform. Now we're going to focus a little bit on 1 through 4 over the course of the next few minutes. But first with battery design. So with battery design, what does that actually mean when I say that we focus on battery design here in this building? The first is what we bring to the table. So from a custom battery perspective, we have a team of expert designers who are ready to jump at any challenge. And when I say any challenge, I mean that we've designed batteries that can go almost to the depths of the Titanic, I believe. We've working on silicon anode-based design that has to achieve the gravimetric and volumetric energy densities required by eVTOL industry. You're actually going to learn more about that today. We're working to design off-the-shelf versions of what we call a JSC 20793 battery. We're going to learn about that later today. But to do that, you have to have the expertise. You have to have the engineers who know how to do battery design, but I would say more than that, who are willing to accept a challenge. A lot of what our customers come to us for when you're dealing in custom boutique batteries is a challenge. They're coming to you because they're struggling to get to that finishing point on their own. They need some help, and that's what we're able to provide with our team. Additionally, expertise, computer-aided design, of course, coming up with designs that we can quickly manufacture in the back with the equipment that you'll see later. And then we do a lot of finite element modeling and analysis. Of recent, we use a lot of thermal desktop. So if you've been in the space business for a while, you know that thermal desktop is a bit of the bread and butter for the modeling industry. You can do a lot of space simulation. It's very good for battery thermal simulations. And then we do a tool called GT Suite, which allows us to do simulation of all the physics that are going on with batteries and also with thermal runaway. So we do work in custom batteries. A focus for 2024, and I would say going into 2025, is continued focus on COTS batteries via the KULR One platform. So we have KULR One Space, we'll talk about that later, which is a focus on off-the-shelf batteries that are certified and ready to operate in space, but designed with intent to satisfy JSC 20793. Our KULR One Guardian platform, a little bit different, focused on DoD applications where you have to satisfy MIL Standard 810H and a gambit of testing that goes along with that. And then we have the KULR One Air platform, which again, we're focused on silicon anode cells achieving absolutely low threshold for gravimetric and volumetric energy densities. So those are the services that we provide with battery design and analysis. We also have a number of products that kind of came to be out of that. We talked about the trigger cell earlier. With each of those, we've naturally developed in-house battery management system, a BMS, which is a key part of our product strategy in 2025. We'll talk about that later. We have our thermal runaway shield, which is used by a number of customers for conductive cell body heating, temperature reduction in the event of a thermal runaway to satisfy their requirements. We've also used it in our space battery platform. And let's see, what else do we have here? We talk about our work instruction 37A screen cells. I'm actually got a slide on that later, but basically providing a cell that has been screened to Work Instruction 37A, where we've looked at mass and dimensional consistencies, looking at electrical performance. We're looking for any defects, corrosion, scratches, dents, doing that in an automated manner so that we can drive costs down on getting the screen cell out the door. So for battery design and analysis, this is kind of what we bring to the table and where we're going. A few of the new things that are going on we'll highlight over the next few slides, though. I mentioned earlier KULR One. KULR One's been a bit of a journey, right? So you come to this realization in 2022, you have all the parts and the pieces and the expertise that you need to start doing your own batteries, but to actually jump in and dive in and start doing batteries and having your own products that you're doing, it takes a little bit of development. And then it's also not just a matter of what do you, KULR, think that you want to do. It's also a matter of what is the market asking you to do. So, we took a long journey looking at micromobility, looking at BESS, energy storage, Powerwall. Again, all the same philosophy: safe batteries, highest quality cells, screen cells. We had early generations of our space battery. All of this we branded as our KULR One platform, but they varied. There was the KULR One, KULR One Max, and then our KULR One Space. However, our contracts took us on a path that matched what our customers were asking us for, which was space, defense, and now air applications. And so really our team here is stacked and poised to support these three areas with off-the-shelf battery solutions or customizable modular architectures over the course of 2025 and beyond. So the first being the KULR One Space. There are 3 series to this battery: a 100 series, a 200 series, and a 400 series. So effectively 100 watt hours depending on cell selection, 200 watt hours depending on cell selection, and 400 watt hours depending on cell selection. All of them designed with a passively propagation resistant design, flame arresting features, which are integral to satisfying JSC 20793. And of course, we have our automated cell line. Each of these batteries are built with fully screened cells. We do a lot of work here. We've had a lot of ongoing work with one of our DoD customers. So we've discussed quite a bit, I think in the public, the work that we're doing for Army DevCom using silicon anode cells. So we're allowed to say that we're doing the work, that we're doing a PPR battery. Can't necessarily discuss the application, but what we can discuss is they need a PPR structure. If you go and you read about DevCom, there's been heavy investment in silicon anode cells. No different with our program. And the goal of our program, this is why I guess you go to events and you network and you meet people. They come to me after one of my talks and they say, so here's the deal, Will. We have these cells. We've invested heavily in them, but silicon anode thermal runaway is really dangerous. Silicon burns a lot hotter. We have some pretty compact designs that we require, and the form factor of the battery can't change because it's going to go into an application. The application absolutely is not changing. So, but ultimately, if we want to see lithium-ion technology and frankly, lithium-ion silicon anode technology into the field, we've got to solve the safety problem. And so that's where KULR came in. The particular battery you see on the screen is the one that we've been working on for them for the past 24 months now. We just did a release. We extended our contract to continue development on that. So this battery will be a key focus of our 2025 roadmap. Similar to JSC 20793, we need to be PPR, we need to be flame arresting, and then they have a gambit of other requirements we have to satisfy, such as ballistics testing, gunfire vibration testing, and a number of other fun tests to satisfy. I'm not going to get too much into the KULR One Air because I don't want to steal the thunder from that presentation. But again, key focus being eVTOL air-based applications, high energy density, low volume, low mass. So that was kind of the vision for KULR One. KULR One started off to be a product, but really it became a vision and a path that we've since followed. Now, I mentioned earlier, and this, for those of you who are in the room and you're trying to learn more about, okay, but on the business side, KULR, you talk about design programs, development programs, but you offer the ISC cell, you offer various services. What else is coming next in the pipeline? One of the things that I'd like to highlight is the battery management systems that the team has been working on very closely. You develop space batteries, you develop DoD batteries, you have to have a battery management system, right? It's a key part of our controls, it's how we operate the battery, and then it also offers protection for us, such as overcharge protection, over discharge protection, current, overcurrent, the list goes on. Then we have passive balancing built in, and you have different needs depending on what environment you're operating in. And so we've since developed BMS that allow us to, on the space side, provide for radiation harsh environments. So we have a fully rad tolerant BMS, certifiable to operate down to T to the -6 or toward the -6 vacuum levels. It can balance 8 parallel strings, and then it has a number of safety features built in, such as current protection, over voltage, and under voltage, and a few other items there. Similar features built into our BMS that we use for our Guardian applications. The difference with this one is it's really set up to be expanded. So this particular BMS can very easily grow up to about 70 volt in capability from a voltage capability standpoint. We can also add quite a few FETs to increase our ability to manage higher current levels and better balancing with those current levels. So part of 25 now is taking these products that we've since developed for programs and now productizing those and making those available as off-the-shelf parts for battery needs. You'd be surprised how many times I've run into a need for BMS that can balance 8 strings and do so in a radiation environment. So we'll be happy to continue developing those in 25 and also be offering those a la carte. On the cell and battery testing, I'm not going to go into too much detail on this particular slide because I actually have more detailed slides for each of these in the deck to come. But the idea is simple here. We wanted to provide a comprehensive testing suite, a comprehensive testing capability to our customer base. Some come in, they need to understand decomposition behavior. Okay, boom, bomb cow. Some come in, they need to understand heat generation because they're getting ready to do a bunch of safety modeling. Okay, great, we satisfy that with fractional calorimetry. Some people come and say, hey, Will, what can you do for me? I love cylindrical cells, but guess what? I'm a large prismatic guy. I got these big cells. What do I do with them? We've got the large format calorimeter, which I'm happy to say we actually did what I believe is the largest FTRC experiment to date, which was over 200 amp hours in cell capacity. So we will continue expanding our abuse testing technologies. We also have plenty of capability for more specialized experiments, such as particle sizing. We had a space customer come to us. They want us to run the calorimetric experiments, but then they said, okay, well, great, that's great, but we got to deal with MMOD, right? And we got to deal with debris in space and all of our orbits, and we got to figure out all this junk coming out of the cells. How big are the particles? So we set ourselves up to do particle sizing for them. We do gas analysis. The list goes on and on. Of course, with electrical testing, we've got a number of Arbin cyclers that allow us to do cell level and module level cycling studies. And then of recent, and this actually fast-tracked since I gave this presentation a few weeks ago, we have onboarded a thermal and humidity chamber, which you'll see in the back, as well as a thermal vacuum chamber, which was critical for particularly our space roadmap. So you're gonna take a look at that later today. Part of our roadmap moving into 2026 will be to onboard vibration table. Key themes in those decisions are to allow us to build, qualify, certify, and do flight acceptance testing for a number of the batteries that we do in-house. So the goal is to drive costs down by keeping as much as possible under one roof. So of course, bomb calorimetry, bread and butter. We have an extended volume calorimeter, so we can do cells that are a little bit larger in capacity. We have this set up for your typical heat weight seek profile, where you're analyzing the decomposition behavior of the cell, looking at your decomp thresholds, looking at onset temperature. We also have a number of in situ sensors that we have been using experimentally, doing in situ measurement of HF, CO, and CO2. And then, we're doing a lot of work studying other techniques that are out there for improving those sensing techniques, such as nitrogen purging, argon purging, things like that prior to experiment. We have the FTRC, NASA's Invention of the Year award-winning technology, an item that I'm very proud of. FTRC is very unique in that, I guess I'll go back and give a little bit of the history, and I'm going to try to keep my eye on my time here. If you go back to 2013, and Sam Russell, if you're in the room, correct me on the time frame if I'm wrong, we have the Boeing 787 Dreamliner incident, battery fire on tarmac, NTSB gets involved, NASA gets involved. Shortly after that time frame in the NTSB investigation of the Boeing 787 Dreamliner, the overarching safety group from NASA headquarters, the NASA Engineering and Safety Center, jumps in and say, hey, we should probably reevaluate our safety criteria for our batteries. We should look at how safe are some of our flight batteries that we have out there, so spacesuit batteries, tool batteries, EVA batteries. And we should reevaluate our requirements for battery safety and just make sure that we're doing things right. And that kind of stemmed following the Dreamliner incident. So that was great. We get involved at Johnson Space Center. The group I was with at the time was focused on doing a lot of modeling activities. I was with an NESC Tech fellow, Steve Rickman. We were focused on doing modeling of thermal runaway and simulating and predicting propagation. And we were trying to use test data to do that, but we kind of had this problem, which was we would collect a total energy calculation from an experiment, and then we'd apply it in the model, and the model would predict propagation every single time, but then the experiment would not propagate. And so we said, what's going on? And then it's that light bulb moment, and I was like, aha, well, crap gets ejected away, right? It's not all just central and local, right? So we have to have a different testing technique. There was nothing out there that could tell us how much heat stays right here in the cell body versus how much is just expelled away. It's a very simple problem, and it's a very simple concept, but there was no testing apparatus at the time that could give us those numbers that we were looking for. So that was the inception of the FTRC, which, as you can see here, has a centrally located cell chamber where we can measure the heat that's coming out of that cell body via thermocouples, and then we can backtrack and calculate out based on the mass of the system, the cell body energy coming out. And then, of course, we have a bore and baffle system coming out of it, which decelerates the flow of the ejecta, prevents flame from exiting, captures any soot and particulate that are expelled from the cell, and allows us to do the mass times specific heat capacity times change in temperature calculation to determine the energy of that ejecta that's coming out of the cell. Now it looks something like this. I'm actually fortunate Peter Hughes did this rendering for me. He was my intern at the time. Yeah, so this one was made a hot minute ago, but this was to characterize the idea of the calorimeter was we have these internal bore and baffle systems which are meant to decelerate the flow of the ejecta coming out of that centrally located cell chamber to where we just have cool gases coming out. And I think the last I remember we calculated it was something like less than 1% of the energy escaping the system on a test-to-test basis in the form of the gases. If you combine the mass of the gases with they on average are about 80 degrees Celsius coming out. It's very, very low energy mist. So we continue today to do FTRC experiments. You're going to see that in the back. And then, of course, the large calorimeter. So this is the bigger brother. Now, we're not highlighting this today, but if you know anybody who needs a really big cell tested and characterized, we're your guy. We can do that. We've done up to 200 amp hours. We also modified the NASA design to be more modular. So you kind of have a big jump, right? If you're in the small calorimeter and you're testing cells up to 10 amp hours in capacity, then you got this big calorimeter that can test cells that are above 100 amp hours in capacity. Well, there's a big range between 10 and 100. What do you do with those cells? Because there's a lot of those cells used in industry today too. So we modified the design to be modular such that we could scale it down in size to allow us to test what we call mid-format cells. Impingement zone mapping is something we do a lot of here, which is where we're focused on characterizing the ejecta coming out of cells. If you really nerd out and dive into the studies of thermal runaway, you're going to find that the early years, and I'm talking all the way back to the 2000s, a lot of the studies were really focused, and in particular on the safety and design aspect, on cell-to-cell propagation prevention. How do I move the heat? Where does it need to go? Do I use a foam? Do I use an insulation? Do I use a heat sink? What do I do? Problem is, you solve that problem, you still got another really big glaring problem, right? Which is about 80% of the heat is ejected away on average. So what do you do with that? So what we're trying to provide with IZM, similar theory to the FTRC, which is a rapid turnaround testing technique that can be low cost that will allow us to trigger with any triggering method out there, any cell that we put into our apparatus and use high-speed videography to provide a visual capture of the ejecta plumes that are coming out so that we can then cross-compare that data to blast plate materials, interstitial materials, various mediums you might want to stick there. Or if you're focused on modeling and you're wanting to focus on the heat fluxes, you don't put anything other than the aluminum backplane, you collect the thermocouple data, and we can do a really good characterization of the localized heat flux coming out of the cell. Now, we typically do this experiment with 3 to 4 cameras or 3 cameras plus a FLIR IR camera. They then get synchronized with lots of Python scripts that are led up by AJ Sauter. I don't know if he's in the room. He's my director of test and analysis services. Special story about AJ, he's also the guy who was our test director for Peter and I at NASA. He made sure that every time we pulled the trigger, we went home with all 10 fingers and 10 toes. So now he's doing that for us here at KULR, as well as a lot of the technical development for our testing services. So we capture that. For customers who do that, we provide the videos, the frame-by-frame analysis, and the heat flux calculations. Of course, what good would a facility be if you can't also test packs and send those into thermal runaway? And sometimes you have a really benign event. You have a successful PPR flame arresting event. Sometimes you have a PPR event, but you got a blowout, so you got to go deal with that. So you characterize the blowout in the test. Sometimes you have full out fireballs. You never know what you're going to expect with thermal runaway, especially when it's not your design. So we're outfitted to support that. Bread and butter, FLIR cameras, GoPro cameras, thermocouples, ability to expand and add on any level of sensors that we want. But what's next for thermal runaway characterization and KULR? So we do a lot of testing. The question we're asking moving into 2025 is how can we provide a better value add for our customers without necessarily increasing the top line price that we're charging to them. Just like with what we're doing with the KULR One Space, driving down the entry barrier, the price point of a 20793 battery, what can I do as a value add for our testing services? And really what it boils down to is why do we test? It's for the data. When you look at the data and when you look at thermal runaway and literally any aspect of thermal runaway that you're characterizing, it's variable. It's highly variable. The amount of gas that comes out, it varies. The amount of heat that comes out, it varies. The amount of combustion, it varies. So on and so forth. Now factor in, it's also going to vary based on your state of charge. It's going to vary based on your triggering method. So what is the best way to help a customer who's only paying for a limited data set? Well, what we're trying to do is fully automate our reporting processes and capabilities so that we can then leverage the time that we then have available to link customer data to other data sets that are available. So one of the things that I had the good fortune of participating in before I left NASA and that NASA has continued to carry the torch on is a publicly available battery failure data bank, which contains statistically significant quantities of abuse testing data. We're asking ourselves, how can I, without impacting the bottom line to the customer, how can I take customer data and automate the comparison of their data to other data that's out there, right? How can I improve my analytics? How can I improve the value of running this one specific test for the customer and giving them insight into how that test compares to other experiments that have been conducted out there, whether that be cell level testing or pack level testing? How can I make data more available? And then how do I build that into the KULR offering or business? So that's a little bit about what's next for our testing services. Now, Michael talked about work instruction 37A cell screening, and he showed the short video. But I run the SharePoint around here. I don't know where all the longer videos are, so I'm going to play the longer video real quick, just to give you a little more insight. What they did here was phenomenal. So Michael mentioned 2018. This one predates me. These conversations. This was really visionary, and what came to be of that is just that a fully automated system that can screen a cell, which by default of using that screen cell, you've thus reduced risk of building packs with those cells, but taken a process that was very expensive, very manual, and streamlined that to a capability with full shifts. We can do on the order of 500,000 cells a year working full shifts. So take a look at this.
Our inspection station is scanning the data matrix and collecting all of the original manufacturer information. We then cut the sleeve off of those battery cells with a laser and remove the sleeve. One of our robots is then picking up those cells and placing them in front of vision cameras where we're doing a visual inspection. After they're inspected, we take the mass of each cell and record that in our database. We then print our own unique identifier on the cell, that's a data matrix, and then place them in a phenolic tray for electrical testing. We then have a large robot which picks up the phenolic tray with 64 cells and places it into our electrical testing unit. The electrical tester is checking for OCV, internal resistance, charge, and discharge capacity. That cycle time takes about 6 hours, and when it's complete, the data is all synced to our database. The large robot places the phenolic tray onto the outbound conveyor. The robot then picks the cells up, scans their data matrix, determines if they are accepted or rejected, and then places them into their boxes.
So, one of the things I want to highlight, again, part of this talk is talking about what is coming in 2025. Michael mentioned the relocation of the cell line to Texas, and that's critical for us. if you look at everything that we're doing here, and then you also look at the designs that we're doing, the testing that we're doing, you look at the cell screening that we're able to provide, there's a central theme. These are all pieces and components of what go into a space battery and in some cases, DoD batteries, trying to get that under one roof. Bringing the cell line here is also very important to us too. Part of what we're trying to do is really institute KULR and make ourselves better partners for supporting the Strategic Reserve, which is hosted here in Texas. Really proud, I think, particularly in the Houston area, being a reserve of energy, whether that be oil, gas. I believe we actually have a reserve of helium. For us, we think it's great, JSC, having the Strategic Reserve here, because now if we bolster that, if we support that, Texas can also be a key part of the strategic reserve for the nation of flight-ready cells for space systems. So we're looking forward to relocating that cell line. Battery production. So Peter Hughes, wave, say hello. This is my Vice President of Engineering on the battery side. Peter's worked really hard to map out our capabilities from a sandboxing and prototyping capability standpoint to a production lab capability for batteries and energy storage systems. So if any of you have ever been in a startup environment where you have this need for engineering sandboxing, but you also have this thing called quality and QMS, there can be a lot of this. And so one of the things that we tried to capture when we built this facility was that we needed to, right? You always have to have a place where your engineers can go and they can do just that, right? They can be engineers, they can tinker, they can put things together, they can try new things. Sometimes things go wrong, sometimes things go right, but they need to be able to do that. I don't want to say untethered, but in a fairly free-flowing manner. So Peter was able to capture that with the battery prototyping lab that you're going to take a look at this afternoon. However, a number of our batteries are kind of at that final stage of qualification. Now it's time to get serious, talk about production. There's a big difference between building off a one-off or even building up, 5 to 10 batteries versus now when you're building 100 batteries, 200 batteries, 500 batteries. So we've built out our production capability, or I should say are building out our production capability in support of expected programs in 2025. So we'll take a look at that. And then, of course, the fabrication that comes alongside of that. You're going to spend some time in our shop taking a look at our CNCs, our lasers, routers, just various prototyping, standard shop stuff. But the idea is for you to walk away with the understanding that if you need a rapidly built part, we can do that here in-house, not a problem. We're, of course, very well versed with working with third-party vendors when we need to. And then during a tour out there, we'll talk about some of the things that we'll be doing with those pieces of equipment to prepare them for more of a production-like environment. Moving to the end of my presentation here, we'll talk a little bit about safe transportation and storage. And I alluded to this earlier. You build a pack, you build a battery. At some point or another, you have to store it safely. You have to transport it. It could be near the end of its life. It could be in a damaged state. It's very common these days, especially with this global push for circular electrification, to have batteries that are in a, let's say, not so pristine state. And what do you do about that? The last thing you want to do is have a battery fire on the floor, or have a battery fire in a charger, or have a battery fire in a truck. None of us, I think, want to end up on the 10 o'clock news. What do you do about that? If you look at a lot of the options that were out there, and if you understand thermal runaway, you look at them and you think this doesn't make sense. This is a cardboard box with qualifications. How does that even make sense? You look at some of the other solutions out there. They work, but they don't necessarily make sense from a handling perspective. If it's all filled up with stuff, it's messy, and then you got to get the battery out, and then you got to clean it off. So that's not ideal. And then if you look at the reporting for a number of the products that were out there, you find that they were satisfied using low energy LiPo cells, or the product was qualified using low energy low thermal runaway response LFP cells. And in a lot of cases, there was not clarity on, well, what was the state of charge? How many cells went off? So we took our safe case product, which at the time had been tested, multiple cells going off, and we said, we're going to take a step back. KULR doesn't want to end up on the 10 o'clock news, and we also want to provide a best-in-class product. So we took the safe case, the Heritage Legacy safe case, we revamped it with thermal liners, optimized shielding, optimized coolant fill of the TRS, which is inserted in the size. And then we forced the teams to go out, and we found some of the most, I would say, packs that would go into destruction very, very easily. Packs that would result in a pretty catastrophic events. COTS packs, things off Amazon, things off Alibaba, you name it. E-bike batteries, scooter batteries, some large format batteries, power tool batteries, and saying, you know what, we're gonna put this thing through the ringer, and we're not done until we're done. And so that's what we did with the Safe Case, which we're happy to do a live demo test for you on today. Right now, it's qualified for up to 2.5 kilowatt hours with supporting documentation and reporting and test reports that stem hundreds of pages. We have it in a number of sizes to accommodate different types of batteries that are out there. We have our sleeve, which can be used for cell phone batteries. You actually need to get a good demo on that from our Vice President of Sales and Marketing, Ted Krupp, later today. That's demo number 4 that you can see on the agenda. He's going to get a lot more into the weeds on why did we do this? Why did we take this on? Why was this a challenge that KULR cared about? And what were we trying to accomplish there with the Safe Case? Again, just really want to highlight here, for us, when we qualified this product, no cell type or chemistry or size was off limits. So we've tested from 18650s all the way up to large format prismatics. As of today, we've done successful testing above 3 kilowatt hours. We're going to go for another push of the envelope 3 kilowatt hour test today. We're doing that for you today for 2 reasons. One, because it's good test data to have and collect, but 2, to show that we stand by our product and that we're always willing to push the envelope. I think when it comes to safety, and in particular the transportation and storage industry, we need more transparency out there on our successes and also on our failures. There's too much out there, I think, people trying to shield themselves and protect themselves and bias tests. For us, we stand by our product. We understand its successes. We understand what's gone on when a test doesn't go the way that we want it to. And we have no problem hopping out and doing tests like this today. One of the litmus tests that we did recently was a test for San Diego Fire Department during a hazmat training event. We're going to do this test. We've got a pack that we're about to package up and ship out to FDMY to do a sub 3 kilowatt hour test with a battery that's been plaguing New York City. We're happy to do litmus testing anytime. But just to give you a sneak peek of what you'll see today, we've got a large format scooter type battery that is similar to what you see in the picture here, large prismatics. This is also a battery that we selected, one, to achieve the energy that we were looking for this particular test. This is our Model R Safe Case. And we'll see how it goes this afternoon. I'm looking forward to it. It should trigger around 3:15, so we'll break from coffee, we'll get the demos, grab a cup of coffee, hop in the conference rooms, or if you go to the back, grab a drink, and we're gonna watch it go off. This is a time-lapse video. It's sped up by about 600 times. So this experiment took place over the course of about 45 minutes for total propagation. And so I think it's really a testament to what the product can do, that it can take a beating for that long a time without the outside or inside failing on us. A lot of work went into the material selection to make that happen. Ted's going to get into that. And hopefully we'll have a good show like this afternoon, which we'll get to follow up with some barbecue. With that said, I appreciate it. I appreciate your time today, and I hope you enjoy your day. So.